First, for this polynomial here, I'm going to let it be fx. So fx will be equal to x to the power of 3 plus px squared plus 6x plus q. And since we are given that 5 minus I is a root of this equation, which means that f5 minus I will be equal to 0. So replacing all the x by 5 minus I, we have a 5 minus I to the power of 3 plus p of 5 minus I square plus 6 of 5 minus I plus q. This is equal to 0. And I'm going to press this and this directly into my graphing calculator to evaluate. And from my calculator, I'll be getting 140 minus 80i. Then plus p of this, which is also what I'm going to be preparing to use my graphing calculator. So with my calculator, I'll get 5 minus I squared as 24 minus 10i. So I have this plus q, which is a real number. This is equal to 0. And I'm going to then group the left-hand side into all the real portions plus I, the imaginary portion. So the real portion will be 140, and then it is going to be this. So it will be plus 24p and q. So plus q. This is going to be the real portion plus I, the imaginary portion, which is minus 80, and then we have a minus 10p is equal to 0. And of course, we can see 0 as if it is 0 plus 0i, which means that we can then match the real on the left-hand side to the real on the right-hand side. Similarly, the imaginary part on the left-hand side to the 0 on the right-hand side. So by matching the real to the real, the imaginary to the imaginary, we will have a 140 plus 24p plus q. This is equal to 0. And the other one is simple. It is minus 80 minus 10p is equal to 0. In fact, we can solve for p directly from here. P is going to be equal to 80 divided by minus 10. So p is equal to minus 8. And if I were to substitute this back into here, we should be able to get the value for q. So we will have a 140 plus 24p, which is minus 8 plus q. This is equal to 0. And this will help us to get the value of q. It is going to be equal to 52. So we have gotten the values for p and q. And with the values of p and q, we can re-express this now. Instead of writing in terms of xpq, we are going to write it in terms of x, and p is minus 8. So minus 8x squared plus 6x plus q, which is plus 52, is equal to 0. So we are now going to try solve this. And to solve this, since we have all the coefficients and they are in terms of real numbers, what we can do is to just simply press this into our graphing calculator. Let me show you what I'm going to be getting from my calculator. So from my calculator, I'll be getting this. So from my calculator, I can see that the answers are going to be equal to this, which means that from here, this here is given to me by the question. X2 here is given to me by the question. So the roots, the other roots that the question is asking for will be minus 2, and the other one is going to be 5 plus I. For the complex number z, we know the modulus is 2 square root of 3. So z is going to be equal to 2 square root of 3. This is the modulus, and its argument is negative pi over 3. So e to the power of minus I pi over 3. So this is the complex number z. And we want to try to re-express z minus 2 square root of 3 into the Euler form, which means that it is going to be 2 square root of 3 e to the power of minus I pi over 3 minus 2 square root of 3. So let's try to re-express this. I'm going to factorize out 2 square root of 3, which will leave me with a e to the power of minus I pi over 3 minus 1. So now we have a form which I have mentioned in the topic outline on Achevas TV, that whenever we have a plus or minus 1, which is here, plus or minus e to the power of I theta, which is this. Okay, let me write it down here. Whenever we have a plus or minus 1, plus or minus e to the power of I theta, a good strategy is to factorize out this. Okay, then we will have a plus or minus e to the power of minus I theta over 2 plus or minus e to the power of I theta over 2, and we will manipulate from here. So I'm going to make use of this strategy for this, since we are seeing this form from what we have already prepared for. So this is equal to 2 square root of 3, and I'm going to factorize out e to the power of minus I pi over 6. So this will leave me with e to the power of minus I pi over 6 minus e to the power of I pi over 6. And the reason why we want to do this is to make sure that we have a pair of conjugates within this bracket here. So with these conjugate pairs, if I were to re-express it into the trigonometric form, this is going to be equal to cosine pi over 6 minus I sine pi over 6, minus away this, which is cosine pi over 6 plus I sine pi over 6. So it is equal to 2 square root of 3e to the power of minus I pi over 6. And for this, cosine pi over 6 and cosine pi over 6 will be cancelled. And I'm going to be left with a minus 2i sine pi over 6. And sine pi over 6 is half, which means that we will have a 2 square root of 3 e to the power of minus I pi over 6. So half times minus 2 is going to be minus 1. So we'll be left with minus I. And minus I got to be re-expressed into the Euler form. So for minus I, if we were to just try to visualize the representation of minus I on an Argand diagram, minus I is going to be represented by a point here, 0, minus 1. So its modulus is 1. The distance of this point away from the origin is 1. And its argument is minus pi over 2. So with this, we can re-express minus I. So we have this e to the power of minus I pi over 6. And minus I will re-express it as 1e to the power of minus I pi over 2, because its argument is this. 1 I'm going to ignore. I'm not going to write it down here. So it will be e to the power of minus I pi over 2. So this is going to be equal to 2 square root of 3e to the power of I of minus pi over 6 minus pi over 2, which will then give us a 2 square root of 3e to the power of minus I 2 pi over 3. And now we have re-expressed z minus 2 square root of 3 into the Euler form, where this is r. So r is equal to 2 square root of 3, and this is the theta that the question is asking for. So theta is equal to minus 2 pi over 3. And now in part 2, we have this divided by this. So I'm going to replace this into its Euler form. So this is going to be equal to 2 square root of 3e to the power of minus I 2 pi over 3. We are supposed to get the conjugate of this complex number, divided by this, which is also 2 square root of 3e to the power of minus I 2 pi over 3 to the power of n. So the conjugate of this will be 2 square root of 3e to the power of positive I 2 pi over 3. And for this, it is going to be 2 square root of 3 to the power of n, and e to the power of minus I 2n pi over 3, which will then give me this divided by this. 2 square root of 3 divided by 2 square root of 3 to the power of n gives me a 2 square root of 3 to the power of 1 minus n. Then e to the power of I, we have a 2 pi over 3. Minus minus becomes plus, plus 2n pi over 3. And of course, we can factorize out 2 pi over 3. So it will give us a 2 square root of 3 to the power of 1 minus n, e to the power of I 2 pi over 3 of n plus 1. And we are given that this is a real number. So in order for me to do this analysis, we can either make use of the Euler form, or we can actually rewrite this into the trigonometric form or the Cartesian form to analyze. I do think that for this particular question, going for the trigonometric form or the Cartesian form is easier. So let me re-express this. So we have 2 square root of 3 to the power of 1 minus n. Then here it is going to be, if I were to re-express it, it is going to be cosine of 2 pi over 3 of n plus 1 plus I sine of 2 pi over 3 of n plus 1. So now we have this. And what is the imaginary part of this? It should be equal to 0 because the question says that this is a real number. So the imaginary part should be 0, which means that this multiplied by this should be equal to 0. So let's try to write it down here. I'm going to let the imaginary portion of this, which is z minus 2 square root of 3 conjugate divided by z minus 2 square root of 3 to the power of n. I'm going to let the imaginary part of this be equal to 0, which is this times this to be equal to 0. And this is always going to be positive, right? So if this times this is equal to 0, that simply implies to me that the sign of 2 pi over 3 of n plus 1. So this must be equal to 0. And again, if I were to refer to what I have on the Achevas TV outline under complex numbers non-Cartesian form outline, when sine of an angle is equal to 0, that means this angle over here is going to adopt a form of k pi, where k here is integer value. So if I have this, making n the subject, n is going to be equal to 3k over 2 minus 1. So let's try to find the various values of n, where k are integer values, by pressing this into the calculator. It is going to make it way easier for us to look for positive integer values of n. So I'll press this into the calculator. Let me show you. So I'm going to press this into the calculator. Okay, this is what I'm going to be pressing. So I'll press this, where k is going to be replaced by x into the calculator. And then from my calculator, this is what I'm going to get. I'm going to generate a table. So for my calculator, if I were to generate a table, looking at my table, I'm just trying to watch out for positive whole numbers for n. So the positive whole numbers will be this, number 2, and this, number 5, and this, number 8. And there are still more numbers. Before that, it is going to be a negative whole number. So that's not what we want. So looking at this, we know the 3 smallest positive whole numbers will be 2, 5, 8. So that's my answer. The smallest, the 3 smallest positive whole numbers of n. These 3 smallest numbers will be, according to my calculator, 2, 5, and 8.